Right. If you can hear me speaking, just reply. Right. Okay. Uh, right. But now, yesterday we were doing some past paper MCQs rotational motion. I think you could not hear properly. I think last two questions that I discussed, you were not able to hear properly. Therefore, I thought of we discuss them also today. Right. So we'll discuss question number in the Pesuru past paper book. Question number 9, right? Question number 9. That means 2011. 2011. 2011. 2011. Right. Uh, Now that question, okay. Flywheel of moment of inertia, 9 kilogram meter squared, about its perpendicular axis through the center is connected to a motor. The motor accelerates the flywheel from rest to 600 revolution per minute, neglecting friction. The work done on the flywheel is neglecting the friction. The work done on the flywheel is. Now, very carefully listen. Flywheel means some sort of wheel, some sort of wheel, right? Then let's say initially this flywheel is at rest. Therefore, initial angular velocity omega naught is 0. We know initial angular velocity omega naught is 0. If omega naught, that is 0. 0. Then they mention that moment of inertia, capital I, moment of inertia of this flywheel, capital I equals 9 kg m squared. 9 kg m squared, right? Moment of inertia of this flywheel. Then you should understand moment of inertia. Now, always when we learn rotational motion and linear motion, we compare linear motion and rotational motion. Now, whatever the physical quantities that we identify in linear motion have some sort of relationship with the physical quantities that we identified as rotational motion. For an example, the moment of inertia in rotational motion. What is the corresponding physical quantity in linear motion? That is we call as mass. Whatever the physical quantity the physical quantity that we identified as mass in linear motion is identified as moment of inertia in rotational motion. Do you understand? So that's very important. You should have some sort of understanding between a moment of inertia and rotational motion, very similar to mass in linear motion. You should have that type of idea. That's very important, right? So then after, let's say, simple t time, after simple t time, angular velocity of the flywheel is 600 revolution per minute. 600 revolution per minute. Final angular velocity omega 600 revolution per minute. Now, revolution per minute. How do we, last day I explained how to convert revolution per minute into radian per second. Revolution per minute to radian per second. If you want to convert revolution per minute to radian per second, we multiply by 2 pi over 60. Multiplying by 2 pi over 60. So therefore, now I have to convert, because I should convert this angular velocity 600 into radian per second. Therefore, I'm multiplying by 2 pi over 60. Multiplying by 2 pi over 60. So then I will obtain 0, 0 cancel out, 6, 6 cancel out, 10 into 2, 20, 25. I am getting 25 radian per second. 25 radian per second. Right? Okay. That is my final angular velocity omega. Now, we should understand in this question, now initially flywheel was at rest. After simple t time, later flywheel has obtained angular velocity 25 radian per second. That means initially when we talk about the energy, initially rotational energy of the flywheel is 0 initially. But now flywheel has some sort of rotational kinetic energy. So what is the equation we learned for rotational kinetic energy? The rotational kinetic energy equation, half half I omega square, half I omega square is the equation that we learned for rotational kinetic energy, half I omega square. Then just think about the linear motion. What is the equation we learned for linear motion to find the linear motion kinetic energy? Linear kinetic energy means half mv square, right? So then initial kinetic energy of the flywheel is 0. If I want to find the kinetic energy after simple t time later, the equation is half I omega square. Now I will find this kinetic energy of this flywheel after simple t time later. Rotational kinetic energy half I omega square, half. What's my I? What's my I? Now I is, now here I is 9, right? Here I is 9. Omega angular velocity 25. 25 whole square. Then I'm getting 9 over 2. 9 over 2. 25 into 25. Right? Then I can cut 1, 2, 1, 2. Then I'm getting here it's 200. 20 into 10, 200. 200 into 9, 1800. 1800 pi square. Am I correct? 20 into 10, 200. 209, 1800 pi square. That is my rotational kinetic energy of the flywheel after simple t time later. Then we can understand. So what happened? Initially, flywheel didn't have any rotational kinetic energy. By using the motor, flywheel has obtained this much of kinetic energy, rotation. Then you should understand how this, now according to conservation of energy, we know that, energy is conserved. Then how this flywheel obtained this kinetic energy? Who produced this kinetic energy? When this motor is rotating, the work done by the motor is converted to rotational kinetic energy of the flywheel. So therefore, in the question, they are asking the work done. But we should understand, according to conservation of energy, we know that work done equals The change in rotational kinetic energy. Do you understand? Work done equals change in rotational kinetic energy. Change in rotational kinetic energy. Now, why now? Change in rotational kinetic energy. Now, final kinetic energy we know. Initial kinetic energy is 0. Therefore, change in rotational kinetic energy equals to this value. Therefore, this is the answer, I think. Right? Now, raise your hands if you understood. So then we'll go to a 2002 A level question. 2002 A level. 2002 A level. 2002. 2002 A level. So I will check exact question number. I will check exact question number. 2002. Question number 47. When you take 2002 A level paper, MCQ paper, the question number is 47. 47. 5 identical uniform rods of length simple L and mass simple M. Mass simple M. Some of which are bent as shown are rotated from rest about a vertical axis. Rods are accelerated until they reach a final angular speed omega naught. Rods are accelerated until they reach a final angular speed of omega naught. Which of the following arrangements requires the highest energy to attain its final angular speed omega naught? Right now, this is very important thing. I don't know how many of you could hear yesterday. I think in case if there is any issue, let me know. Right. The first important thing is now inertia. Now in linear motions, we are talking about inertia, right? But when it comes to rotational motion, we are talking about moment of inertia, right? So what's the idea of inertia? Inertia means we learned that the tendency to resist the state of lift, the tendency, there are some objects, no matter it's linear motion, rotational motion, all the objects, they don't like to change their current state of motion. For an example, if an object is at rest, that object likes to keep its state of motion at rest. If an object is moving, that object does not like to change state of motion. That means, let's say an object is moving under constant velocity. That object does not like to increase its velocity or decrease its velocity. Do you understand? Let's say an object is rotating under constant angular velocity. That object does not like to change its state of motion. That means that object does not like to increase its angular velocity or decrease its angular velocity. That's the important thing, right? Now, when it comes to linear motion, we are saying about that inertia. What is the physical quantity which measures the inertia in linear motion? In linear motion, the inertia is measured by the mass, right? In linear motion. Then we can say that inertia means some sort of resistance to change the current state of motion. Very carefully listen. Inertia means some sort of resistance to change the current state of motion. Object is at rest, like to stay at rest. Object moving under constant velocity, like to move under same velocity, right? Large the mass, the quantity, the physical quantity which measures the inertia in linear motion is mass. In mass, I'm talking about linear motion, right? Linear motion, mass. Large the mass, we know that inertia is large. Smaller the mass, inertia of the object is smaller. For an example, let's just consider a huge rock and a small stone. Rock is having larger mass, therefore we can't easily move the rock, right? If the mass is very smaller, by providing an even small force, we can easily move that. We can change the state of motion. Stone is at rest, rock is also at rest. If now which one shows larger resistance to change the state of motion? Larger mass rock. That's why, because rock is having large inertia. Very similar idea. Very similar idea. If you need to change their state of motion, you should provide larger force, larger effort. Very careful, this is the important thing. If you want to change someone's state of motion, the object having large inertia, if you want to change that object state of motion, you should provide a large force. You should do a big effort by providing very large force to change that object state of motion. When object's inertia is larger, the effort that we put is also large. That's the idea. So this concept is valid not only for linear motion, but also it is valid for rotational motion. Now in linear motion, what is the physical quantity which decides the inertia? In linear motions, mass is the physical quantity which measures the inertia. Large the mass, large the inertia. But when it comes to rotational motion, inertia is measured by moment of inertia. Now when it comes to rotational motion, moment of inertia is the physical quantity which measures the inertia. So mass, moment of inertia depends on mass and axis of rotation and mass distribution. But when it comes to linear motion, only mass was the factor which decided the inertia. When it comes to rotational motion, not only mass, but also axis of rotation and also mass distribution will affect the moment of inertia, capital I. Now, I can explain this MCQ, but generally my intention is to remember and give some additional point regarding its MCQ. Now, in rotational motion, moment of inertia depends on main three factors. Mass is one of the factors, then axis of rotation. Axis of rotation. The last one is mass distribution. Not only mass, but also mass distribution. Today we will do some MCQs related to mass distribution. Even some objects have same mass, but if their mass distribution is different, then also moment of inertia is different. Mass distribution. Mass distribution. Right. Now in this given question, now what they say now, there are same mass. Now all these 5 objects have same mass, right? All these 5 objects have same mass, right? All these 5 objects have same mass. Now somehow we should bring all of them to same angular velocity. Now they have same mass, but the thing is their mass distributions are different, right? All of them have same mass, but their mass distribution is different. Somehow we should bring them to same angular velocity. Question, we should find which of the following arrangement requires the highest energy to attain its final angular speed. In order to bring all of them to same angular velocity omega naught, to which object that you should provide a large energy, to which object that you should provide a large effort. Then you can clearly understand the one having larger inertia requires larger effort. The one with the largest inertia requires larger effort. That means a larger energy. Larger energy. Now, if you came to this conclusion, the one with the large inertia requires larger effort, then you can easily get the right answer. Now, all of them have same mass, then you should check the mass distribution, right? How do you check the mass distribution? Just think that how long mass has distributed. Then when you consider all those five objects, which one is having larger mass distribution from the axis of rotation? From the axis of rotation, which object has larger mass distribution? Just find the largest length from the axis of rotation. Reply, everyone reply, which object has larger mass distribution out of those five objects? If you want to check about the mass distribution, larger mass distribution, just check from the axis of rotation, which object is having larger length. Then that object has the largest mass distribution, right? Then you can clearly understand object number five is the answer. Do you understand? Raise hands, how many of you understood? So then that question is also done. Okay. Uh, right. Then this question. Question number 11, 2003 11. 2003 11. 2003 11. Next question. 2003 11. 2003 11. Question 3. Question number is question number. Wait, give me a second. Question number. Question number 30. Question number 30. Question number 30. Right. Now this case, what is the question? Uh, two uniform rods, capital A and capital B, having same dimension. They are having same dimension. That means same length, width, breadth. They have same dimension. Made of different materials. All right. Now, if they have same dimension, what is the conclusion? Now reply now. If they mention now there are two objects, both objects have same dimension. Then what would be the conclusion? If both of them have same dimension, what will be the conclusion that you come? Reply. What will be the conclusion? Reply. The conclusion is both of them have same volume. Conclusion is both of them have same volume. Right. Same dimension means both of them have same volume. So axis of rotation. This object capital A. This one is object capital B. Now they mention both of them have same dimensions. Then volume is same. Volume same both of them. But both of them made with two different materials. So therefore both of them, the density of capital A. It's lagging. Reply. It's lagging reply. Yeah, why others can't reply? If you can't reply, my advice is leave from the session. The people who can't reply, just leave from the session. You don't need to stay. Just leave from the session. You can call the past papers by your cell phone, right? Therefore, leave. So always same one replies all the time. You can leave. Something additional thing. It's not theory part, right? It's some kind of question discussion is not important. Therefore, leave. Leave. Don't stay. Leave everyone. Can't reply. Give me a second. Now it's fine. Someone reply. Now it's fine. Still it's lagging. Right. Okay. Now in this case, now they mentioned both of them have same dimensions, means both of them have same volume, but but their masses are different. Why? Their density different. Density of capital A is dA. Still lagging. All right. Density of capital A is dA. Density of capital B, that's dB. We can come to the conclusion. So we can come to the conclusion that when they have different densities, their mass is different because they have same volume. They have same volume, but density different. Therefore, their mass is different, right? They have different masses. Mass different. I say me this one mass in, right? Right. Okay. Then the question they are asking two uniform rods A and B having same dimensions but made of different materials of densities dA and dB rotate as shown in the figure. If the rotational kinetic energies of the rods are same, they mentioned rotational kinetic energy same. Both of them have rotational kinetic energy. I say capital E, capital E. Both of them have same rotational kinetic energy. Capital E, capital E, capital E, capital E. Right. Okay. So what is the equation involving rotational kinetic energy? We can say half I omega square. That's the equation we apply. In this case, they are asking angular momentum ratio A to B. Angular momentum means capital L, capital L. Now, can you remember when we were discussing linear motion, we derived three equations for kinetic energy. I'm talking about linear motion. Half mv square. What are the other two equations? In terms of momentum, linear momentum and mass, half p squared over simple length. What is the other equation? Right? In half, what are the equation? Half mv squared, p squared over 2m, half, what is the equation? PV. Am I correct? PV. Then likewise we can obtain equations for rotational kinetic energy as well. Rotational kinetic energy equals half, simply mass in rotational kinetic energy, moment of inertia, half I, velocity in linear motion. When it comes to angular motion, rotational motion, angular velocity omega square. Then rotational kinetic energy equals half P, linear momentum. When it comes to rotational motion, angular momentum L squared over mass in rotational motion, that is inertia I. So likewise here, half L omega, right? You can remember these things, all these things, right? So then I will use this side, I will side. So then we know that rotational kinetic energy proportional to L squared over I. We can write down this way, E equals L squared over I. So then I can write down for this one. Now, I just do with all the steps, but coming days in paper classes, I will read the steps. Now I can consider this first object and I can write down capital E equals half L capital A squared over L capital A squared over moment of inertia of first one. Their mass different, IE, equation 1. Then if I apply for capital B, rotational kinetic energy equals half LB squared over IB, equation 2, right? So then I can equal them, then I will obtain that. I can write down, if I equal them, I can write down LA squared IA equals LB squared over IB. Now I need to find LA to LB ratio. Angular momentum of A to angular momentum of B, LA to LB. LA to LB. LA to LB. Then I can write down LA to LB equals IA to IB. IA to IB. All. Then we know that now. Both of them, let's say both of them are rods. Both of them have same volume. So therefore we know that somehow moment of inertia equals kind of constant mass L squared or something. So therefore now both of them have same dimension. So therefore moment of inertia only depends on mass. Do you understand? Moment of inertia in this case only depends on the mass. They have same axis of rotation, they have same dimension. Therefore moment of inertia only depends on the mass. Mass only depends on the density. Why? Volumes are same. So mass depends on the density. So therefore I can write down moment of inertia ratio. IA to IB, we can write down as DABB. Why? Moment of inertia only depends on the mass. Mass depends on the density. Volume same. So therefore I can write down IA to IB ratio equals DA to DB ratio. This is the answer. That question. Raise your hands. How many of you understood? Raise your hands if you understood this question. Because moment of inertia, capital I means anyway, some kind of constant mass, some kind of length. So R squared, L squared, L squared, R squared. Both of them have same dimension. Therefore, L is a constant. Moment of inertia is proportional to mass. This idea. Then we know mass over volume is density. right? Volume is constant for both of them. Therefore, mass is proportional to density. So that idea. So then next, then that question is also discussed. Then we'll go to 2004 A level. This is a very important question. 2004 A level. It's very important. 2004 A level. Give me a second. So when you hear lagging, let me know again. 2004 A level question number 18. Question number 18. Question number 18. Now I told you, even though, look at it. Now there are some objects. This is very important point. Please include whatever I'm going to say in your short notes. This is very important point. It's very, very important point. Include this idea in the short notes. Right? Okay. Right. Now we know that, just say now there are three objects. Now all those three objects have same mass, they have same dimensions. Right? There are three objects. They have same mass and same dimension. For an example, let's consider some disk type objects. Now in the diagrams also they have given three types of objects A, B, C. A, B, C. A, B, C. A, B, C. Object capital A. Capital B is a disk. A disk. It's a very important point. So therefore put this in your short notes. Disk. Capital B. Or capital C. Capital C seems like a bicycle wala in rim method. Paddle එක හරියට මේ වගේ we can see center some kind of design. So we can see some kind of design. Yeah, I don't know the exact shape. We roughly can understand the object. The interesting thing is talking about A, B, and C. All those three objects they have same mass. They have same radius. Same radius means same dimension. All of them have same dimension. But the thing is, mass distribution is different. You know why? Now sometimes now right now the idea regarding mass distribution that you have is from the axis of rotation. If a rotating object has larger length, you can say that its mass distribution is large. Now, you know, when you consider all these three objects, their axis of rotation is to the center. No matter, all of them have same mass and their mass distribution, if not the length from the axis of rotation to the last drop of the mass, from the axis of rotation, the length of the mass distribution, last drop of the mass, all of them have same. They all have same. But understand, Previously, I told that mass distribution depends on the length from the axis of rotation. That's also one important point put in a short note. Mass distribution depends on the length from the axis of rotation. That's important. And also mass distribution depends on the mass concentration. Mass distribution depends on the mass concentration. If more mass is concentrated more away from the center of rotation, very careful to understand. If more mass concentrated away from the center of rotation, then that one has larger mass distribution. Very careful, listen one last time I'll say that. If there are objects, if their mass distribution is more away from the center, if mass distribution is more and more away from the center, then understand that one is having larger inertia. Do you understand? So everyone reply, out of these three objects, all of them have same mass. Which one has larger mass distribution? Reply. Which one has larger mass distribution? Reply. Which one has larger mass distribution? Reply. Obviously, capital A. When you consider the entire simple mass is concentrated more away from the center of rotation. Now, when you consider the second object, evenly distributed. Mass distribution is evenly distributed. For this one, comparing this one, larger mass distribution, but this one is having smaller mass distribution. Do you understand? So therefore, which one? Larger mass distribution means larger inertia. Large inertia means in the question they are asking. Order that they will reach the bottom of the inclined plane as the first, second, and third respectively. Now we know that large inertia, right? Now these three objects have different inertia. Then if I rank them, this one is having large inertia. Small inertia belongs to B. Inertia of B is smallest. Then second large inertia belongs to C. Large inertia belongs to capital B. This is the variation of inertia, moment of inertia. Now we know that one is having large inertia. The one which is having large inertia comes at the end because it does not like to move. The one is having small inertia likes to move. Do you understand? The one is having small inertia quickly move. That means its velocity is high. One is having smaller inertia quickly move, velocity is high. One is having large inertia, velocity is low. Therefore, tell me what is the right answer. Everyone tell me what must be the right answer. Reply. What must be the right answer? Everyone reply. Quickly. Reply everyone. Second one, how many of you say raise your hands? How many of you say second one is the answer? Second one is the answer. That's the idea now. So the important point that you should write regarding this MCQ is mass distribution depends on the length from the axis of rotation. Next important thing is mass distribution also depends the mass concentration. If the more mass concentrated more away from the center of rotation, that object is having larger inertia. Next important thing is larger inertia means we need to provide large energy. One is having large inertia, does not like to move. It's moving slowly, right? If it is moving slowly, means it takes long time. That's the idea. That question is done. Then we'll discuss. Next one, 2005 A level. 2005 A level. Right. Okay. The uniform circular disk of radius capital R and capital M rotates the uniform angular speed omega. Okay. Right. Okay. 2005 A level. Question number 2005 A level. Question number 38. The paper, the real paper. 2005 A level, question number 38. 2005 A level. Question number 38. Now it's about conservation of angular momentum. Now last day also, I explained what is conservation of angular momentum. What is the idea? When there is no external torque, when you're talking about angular momentum, mention about the torque. When there is no resultant torque, angular momentum is constant. That's the idea. Now what they say in the question they say that uniform circular disk of radius capital R and capital lim, circular disk of radius capital R and capital lim, rotates with a uniform angular speed omega in a horizontal plane about an axis passing through its center perpendicular to its plane. Disk M and R. Disk M and R. Disk. Right. Axis of rotation. Mass capital lim. Mass capital lim. Radius capital R. They mentioned angular velocity. So what is the angular velocity? What is the angular velocity? Angular velocity is. So do you hear some sort of reduction in my voice? Reply. Do you hear some sort of reduction in my voice? No reduction. They mention angular velocity is omega. So then what? Then they are talking. Then they say that uh, the moment of inertia of the disk about the axis described above is half mr squared. Now you know if it's a disk, I think I gave the note. If it's a disk, what is the moment of inertia? Half mr squared. We know that idea. When a ball of clay m/8 placed gently means slowly. Ball of mass m/8 placed gently on the edge of the disk. If it sticks the new angular speed of the system, it's very similar to linear motion angular momentum scenario. Now, for an example, this idea. Let's say now there are two masses. Now, one mass is, let's look at the calculation. One mass is at rest, m1. Now, one mass is moving towards m1 with a velocity of capital V. Just before collision. After collision, they stick together. After collision, they combine together. Then the velocity, the total mass m1 plus m2, their velocity will be v1. How do you find v1? Apply conservation of linear momentum. All. Then before total momentum means mv must be equal to after total momentum m plus m1 v1. Very similar idea. Apply conservation of angular momentum in this case. Why? Because they told that gently they are placing a clay on top of the edge of the disk. On the edge of this, they are gently, smoothly, without producing any resultant torque, they place the clay. You have to very carefully understand. Now this time it is your clay. Exactly at the edge of the disk. Now we know radius of the disk is capital R. Now tell me now, look at here, very carefully listen. Now same disk. Initially, disk having mass simple m radius capital R rotating under angular velocity omega. Now what happens when a clay mass is capital M/8 gently placed at the edge of the disk? What would happen? Raise your hands. How many of you say that? When now this time now clay sticked also. This clay sticks with the disk continuously. This entire system is rotating. Raise your hands. How many of you say after clay stick together with the disk, moment of inertia has risen? When clay stick together with the disk, moment of inertia of the system has increased. Raise your hands. Raise your hands. How many of you see moment of inertia of the disk has risen? Entire system is risen, increased? Yes, increased. then what would happen for the angular velocity? Reply everyone, then what would happen for the angular velocity? What would happen for the angular velocity? Reply. So when the moment that you hear my voice is breaking, quickly let me know, decreases. Why? Because there is, we didn't apply resultant torque. Because gently simple mass placed on the edge of the disk. Therefore, we know there is no resultant torque. No resultant torque. If no resultant torque means we can apply conservation of angular momentum. Oh. So what is the total angular momentum before the system? Total angular momentum before capital M, we know what is the equation to find angular momentum? The linear momentum P means MB. Linear momentum P means MB. Angular momentum L means I omega. I omega. Then there is only one disk. Simply mass is at rest. Sorry, MO8, your clay is at rest. Then angular momentum equation. I omega. I omega. I omega. Before angular momentum means I omega. I say I1. This angular momentum of the disk is I say I1. Angular velocity is omega omega. Angular momentum of the system after clay ball stick together with the disk. I say I2. Then corresponding angular velocity, I say omega 2 something else. Omega 2. And then we can apply conservation of angular momentum. Before angular momentum is I1 omega. I1 omega must be equal to, after system's angular momentum is I2 omega 2. Omega 2. Now you know the angular momentum of the disk. What is the equation they given? Angular momentum of a disk is half what m r squared, half m r squared. I1 is, we can say that half m capital R squared omega. So what is the total angular momentum of the system after clay ball stick together with the disk? Angular momentum of the disk half capital M R squared plus angular momentum of the clay. This kind of clay simple. We can say this clay as a point mass. This point mass is moving in a rotational motion. Then tell me what is the equation of angular momentum? So what is the equation to find the moment of inertia of the clay mass? Tell me what is the equation that we use to find the moment of inertia of the clay mass? mr square. mr square. The mass is m over 8. Radius same as r. The radius distance to the clay ball is same as r. Distance to the clay ball from the center of rotation, capital R, mr square. Omega 2. Omega 2. Then you can simplify. So you can simplify here now. I can take mr square and I can cut all the mr square terms. Then I am getting here omega over 2 equals half 1 over 8. Half 1 over 8 means if I multiply this one by 4, 4. Then I'm getting 4 plus 1, 5 over 8. 5 over 8. Omega 2. 5 over 8 omega 2. So then I will obtain my omega 2 equals omega 2 equals 4 over 5. 4 over 5 omega. Am I correct? So if I did the simplification correct, I did the answer. If you understood, raise your hands. If you understood, raise your hands. Right, okay. In that question also discussed. Now, this one is very important question. 2006 A level. It's very important question. 2006 A level. Right? 2006 A level. right? My voice is very clear without any echo or anything. My voice is very clear. Reply someone. It's very clear as usual. Usual way, it's very clear as usual way. It's very clear. You don't hear any sort of difference, right? Okay. 2016. Then we are doing hydrostatic basket. Likewise, with 2006. Then 2006 question number will be question number 58. Generally understand when the question number is more than 40, you should understand that question is difficult question, right? Please now, generally those all syllables, there were 60 MCQs in the paper. Now sometimes there can be questions number 55, 56, 57. This question number is 55, 55, 55, right? It's a very good question. It says that, this question says that circular disc shaped pinwheel type firework shown in the figure performs a rotational motion about Z axis. Performs a rotational motion about Z axis on the horizontal smooth flow due to constant reaction force generated by its burning. The first important thing you should notice is constant reaction force. Constant reaction force. F is constant. So you should understand where this F is applied. You should understand that one also. Okay, right? Assume that the pinwheel power the shape of a uniform circular disc throughout and its moment of inertia is half mr square about z axis. If mr, omega, and alpha are the value of mass, radius, angular velocity, and angular acceleration respectively, of the burning pinwheel at certain instant, then okay. Now, now try to explain. I will try to explain this way. Before you come to this session, you must have done these MCQs before at least one time. It's your job, right? Uh, Generally, normally hereafter, these sessions will be on 10:30 p.m. to 12. Today I started 9:30 because I could not do today online class properly due to issues. I will draw only 3,000. Now, our Bamara Chakra, we say Bamara Chakra, Bamara Chakra, 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 Ratinga Magidin Chakra Mangitan. I don't know in English what we say. Now, usually we fire exactly this H, right? We exactly fire this H. So when we burn this H, what happens? What happens? There will be a reaction force on the firework. When we burn this H, understand there will be a reaction force. Now you might have burned. Now tell me if you burned in this way. Raise your hands. How many of you say this firework will move in clockwise direction? Now you might have burned these things in your childhood. Raise your hands. How many of you say if we burn exactly this H, if we burn exactly this H, This firework will move in clockwise direction. Raise your hands. Firework will move in clockwise direction. Raise your hands. Raise your hands. How many people say anti-clockwise direction? That is obviously clockwise direction. Why? Because when we burn exactly here, the reaction force acting on this edge will be capital F, in this way. So because of this reaction force on this firework moving clockwise direction. Why? Because of this capital F, there will be a torque in clockwise direction. Am I correct? Right. Radius given as capital R. Radius given as capital R. Mass of this firework is simple limb. Simple limb. What else? Z axis. Z axis. Z axis coming through the center. Yes. Yeah. Angular acceleration alpha. Angular acceleration alpha. Angular acceleration alpha. Right. Angular acceleration alpha. Right. Alpha. Okay. Right. Okay. Angular velocity omega. Angular velocity omega. Now, this is not difficult thing, but sometimes if you didn't notice that constant force, there will be a problem. Now, because of the when we burn exactly this edge, what happens? There will be reaction force on this firework in this direction. Because of this capital F force, it creates some kind of torque. Because what is the equation for torque? Torque means force into perpendicular distance. So equals F into capital R. This time F into capital R. Torque. This is the equation that we learned for torque. So because of this reaction force, there will be a torque in clockwise direction. Therefore, this firework rotates under acceleration because there's a torque. There's a torque. If there is a resultant torque, it seems like there's a resultant force on a mass. If there is a resultant force on mass is accelerating. Then if there is a resultant torque on a firework, the firework is accelerating. The angular acceleration, undergo angular acceleration. Undergo angular acceleration. Right? Right? Because of this resultant torque, this firework undergoes angular acceleration alpha. Right? Okay. Now they mentioned this capital F is constant. They mentioned this capital F is constant. Right? We know equation for the resultant torque is tau equals F into R. If not, we know one more equation for torque. Reply. What is the other equation that we learned for the torque? One equation to the torque is resultant torque means F into R. F into R. There is another equation to find the resultant torque. Reply. What is that? What is the other equation to find the resultant torque? I alpha. I alpha. Tau equals I alpha. Tau equals I alpha. I alpha equation. Right? Based on these two equations, I can write down equation 1, equation 2, I can write down. I alpha equals F into capital R. Then they given what is the value of I? Half m R squared. The value of I, half m R squared. I means half simple m R squared alpha F into capital R. Then R, 1 R cancel out. Then we are getting capital F. Capital F equals half m R alpha. We are getting something like this. Now in the question they clearly mention capital F is always a constant. If capital F is always a constant, half multiplication of m into r into alpha is a constant. Raise your hands. How many of you understand if capital F is a constant, multiplication of m, I'm talking about multiplication of m into r into alpha is constant. Raise your hands. How many of you understand? Raise your hands. But if you ask that now, when mass decreasing with the burning mass decreases, sometimes R also decreases. I think acceleration increases. In that way, they become constant. So half mr, half mr alpha constant. That means mr alpha is a constant. That right. Raise your hands if you understood. If you understood, raise your hands. So then that is also done. Then look at that question number 15. Now it's very good question. 15. Next one. 2007 A level. That's also a very good question. 2007 A level. That's a good question. 2007 A level. Question number 24. 20, 24. Right. The two uniform discs capital A and capital B shown in the figure are made of the same material. Same material have equal masses. Same material have equal masses. Same material have equal masses. Now, two uniform discs A and B shown in the figure are made of same material, have equal masses. Then tell me what is same. If both of them made the same material, we know density of both A and B is same. They mention mass is also same. Then tell me in addition to mass and density, what is same for both of them? In addition to mass and density, what is same for both of them? Reply someone. Volume is volume is. So for an example, capital A is having larger cross section, smaller thickness. Capital B is having smaller cross section, large thickness. Somehow volume is same. A into it same. Then the radius of the disk capital A is greater than that of capital B. Discs are kept in isolation outer space. Consider the following statements. Capital A. If I do those two, this compulsory. This A or this B. Now there are three statements: capital A, capital B, and capital C statements. The disk capital A takes longer time than capital B to gain given speed under an external force. This is very important. Now most of you, okay, I will ask that. The disk capital A takes a longer time than capital B to gain a given speed. That means given speed, gain a given speed under an external force acting through the center of the disk. Raise your hand. Just read carefully. I'm expecting an answer from everyone. Raise your hands. How many of you say that capital A statement is correct? Raise your hands. How many of you say that capital A statement is correct? Raise your hands. How many of you say capital A statement is correct? Capital A statement is wrong. Raise your hands. How many of you say that capital A statement is wrong? I don't get any reply. Raise your hands. How many of you say capital A is correct? Right? Capital A is right. Raise Capital A is wrong. Capital A is wrong. Raise wrong. Capital A statement is wrong. Why? Capital A is wrong. Why? The thing is now they are talking about now. Both of them have same mass. Same mass. Both of them have same density. They have same volume. But dimensions are different. This one's area is A1. This one's area is A2. Its length is L1. This one will be L2. Now, however, multiplication of A1 to L1 equals A2 to L2. These volumes are same. Cylindric, right? Now they say that now applying now capital statement says that clearly. It says that this capital A takes longer time than capital B. Capital A takes longer time than capital B to gain a given speed. Not they are not talking about angular speed. They are talking about given speed under an external force acting to the center of the disk. That is, capital A takes a longer time than capital B to gain a given speed under an external force acting through the center of the disk. Now, when we apply a force to the center of the disk, do you think this disk will rotate? They don't rotate, right? If you provide a force to the center, if you provide a force to the center, what would happen? Disk won't rotate, disk will move. So when we provide a force to the center, disk won't rotate. Disk will move in linear motion. Then we learned that. We learned generally to gain a particular speed. Now let's think about linear motion. Now today also I explained. When we consider linear motion, inertia, generally the one having large inertia takes longer time to obtain a particular speed. Am I correct? The important short-term points. Generally, an object having larger inertia takes longer time to obtain a particular speed. Then, in linear motion, we know that moment of inertia. Linear motion, we know that moment of inertia only depends on the mass, not about the mass distribution or anything else. Not about the axis of rotation, linear motion. Because of these forces applied through the center, these disks move in linear motion. If both of them have same mass, they have same moment of inertia. They have same inertia. If both of them have same inertia, they take equal time. Therefore, capital A is wrong. Capital B, capital B. The disk capital B takes a longer time than capital A. The disk capital B takes longer time than capital A to gain a given angular speed. To gain a given angular speed. In that case, now we know that now out of these two, which one is having large inertia? Reply now. When both the disks are rotating, which one should have large inertia? Moment of inertia. Reply everyone. Which object has larger moment of inertia when you consider these two objects? Reply everyone. Because this one's mass distribution spread long. When you consider these two, this one's mass distribution has spread long. Capital A has large moment of inertia. Capital A has large moment of inertia. If capital A has large moment of inertia, capital A takes long time to come to a particular angular speed. If capital A takes longer time to come to a particular angular speed. But they told this B takes longer time. This B takes longer time than capital A to gain a given angle. That's wrong. That is also wrong. That is also wrong. See, that this capital B has a higher rotational inertia about the axis. This capital B has the highest rotational inertia about the axis of the disk than disk A. C is also wrong. The disk capital B has the highest rotational inertia. Capital B has the lowest rotational inertia. Therefore, capital C also wrong. Answer is 6 1, 2007. Answer is fifth one, I think. Answer is, give me a minute. 24. Now, someone please tell me how many questions that we discussed today again. How many questions that we discussed again? All are wrong. Discuss 7. Then next one, 2007. That is also 2007 question. 2007 question number, that is question number 28. This one is 28. 28. Question number 28. 28. Now, what this question says. Now, up to now, did you hear any reduction in my voice or any lagging reply? Up to now, did you hear any reduction in my voice or any lagging reply? No reply. No, no, okay, no. No. In this case, starting from wrist, a sphere takes a time simplicity to roll down a rough plane. If the plane is made frictionless, this is very important. The time taken by the sphere to slip down will be. Now, this is also a very tricky question. Now, they mention now two inclined planes, sphere, inclined plane, okay? Roll down a rough plane. Okay? Starting from where the sphere takes a time simplicity to roll down a rough plane. Okay, they didn't mention about incline, but they mentioned rough plane. Okay, look at, let's consider inclined plane. Inclined. So both of them, let's assume both of them have same inclination. Both of them have same inclination. Initially, our sphere at the same elevation, same height, simple pitch, same height, simple pitch, same height, simple pitch, same height, simple pitch. Right. In this case, now we'll come with the conservation of energy. The one difference between first and second diagram, the only difference is first diagram is rough plane, second diagram is smooth, rough and smooth. Rough, second one is smooth, right? Then what happens? When plane is rough, what would happen for the motion of the sphere? These are important short note points. When the plane is rough, what will happen for the motion of sphere? That sphere is having obviously kinetic energy, linear kinetic energy plus sphere. They roll on rough planes. Do you understand? Rolling occurs in rough plane. So therefore, the sphere moving along this rough plane have two types of energy, right? That means, let's say now, what will happen? When this initial starts from rest, when this sphere moves along this rough plane, what will happen to its gravitational potential energy? Decreases. That gravitational potential energy converts to linear kinetic energy plus rotational kinetic energy. Important. Initially, sphere was at rest. It was only having potential energy. But when that sphere is rolling down, now this time it is having linear kinetic energy plus rotational kinetic energy. Let's say the sphere has reached the final point. Then what happens? Total kinetic, very carefully listen. Total gravitational potential energy converted to linear kinetic energy. At this instant, linear kinetic energy plus rotational kinetic energy. careful understand. Second diagram, if the plane is smooth, there won't be any rolling. If object is not rolling, object does not have any rotational kinetic energy. Your object is slipping. Your object is slipping along this plane. Then object is only having rotational kinetic energy. You understand? Then object is slipping. Then object is only having linear kinetic energy. Then entire, when you consider conservation of energy, gravitational energy decreases, linear kinetic energy increases. When the object is at here, total gravitational potential energy converted to linear kinetic energy. Then you can clearly understand when you compare these two diagrams. Reply me. Which case? I see it's on case 1. This is case number 2. Now tell me out of these two cases, which case sphere is having larger kinetic energy? Reply. By looking at this equation, you can tell exactly which case sphere is having larger kinetic energy. Reply. Reply everyone. When you compare these two cases, which case object is having larger kinetic energy? Larger kinetic energy. Large kinetic energy. I'm asking large kinetic energy. This is constant. 500 means 500. 500, 500. 500 converts to 500 linear kinetic energy, case 2. But 500 converts to only 300, only 400, only 250 to linear kinetic energy. Therefore, linear kinetic energy is larger in this diagram. This one. Larger linear kinetic energy means larger velocity. Larger linear kinetic energy means understand. Larger velocity. This object is going very fast. The object is going very fastly. Time is small. Yeah, you know that. This case, comparing the time taken to move from here to here in rough plane, time taken to move from here to here in smooth plane is small. Raise your hands, how many of you understood? Raise your hands, how many of you understood? If you understood, raise your hands. Right. The next one. Next one, 2007, question number 28. 28. 20. This must be 24. This must be 24. It's 24. This question is 24. This is 24. I think it's not 24. It must be something different question number. I think. Wait, I will check exactly. 2007. This question. That is 20. This is 28. This is 28. This question is 28. The next question that we are going to discuss is question number 44. Next one is 44. Next one is 44. Next one is 44. 44. If you hear some sort of lagging or breaking, when the moment that you observe it's lagging or breaking, let me know. Battery might go into dips. Right. At what time we started the session? 9:30. 9:30, 9:35. Now this question, number 44, says that. Now here is also you should apply conservation of angular momentum. As shown in figure, capital A, child is sitting on a rotating chair. Rotate the angular speed omega. Moment of inertia of the system with the child around the axis of rotation is 2 kg m square. 2 kg m square. 2 kg m square. This seat. Child. Child right? Okay, right. Now speed omega, omega. Total moment of inertia of this child along with all the instrument is they given. I say I1 is 2 kg m square. I1 2 kg m square. In this case, moment of inertia system with the child around, okay, as shown in the figure B, while rotating the child catches a thin ring capital B of mass 4 kilogram. Ring capital B of mass 4 kilogram. This ring is having a mass 4 kilogram. So tell me what is the equation that we learn to find the moment of inertia for ring reply? What is the equation that we learn to find the moment of inertia for ring reply? What is the equation that we learn to find the moment of inertia for ring reply? What is the equation we learn to find the moment of inertia for ring reply? Is it half mr squared mr squared? Others? It's half mr squared mr squared. Reply quickly. Quickly. Replies everyone. The moment of inertia for ring. Half mr squared or mr squared. Reply everyone. It must be half mr squared. Half mr squared or mr squared. It's mr squared, I think. 4 kilogram diameter is 1 meter. It is mr squared. It's not half mr squared, it's mr squared. Moment of inertia for ring is mr squared, right? Mr squared. Diameter is given 1 meter. Then what is the diameter? What is the radius of the ring? Radius of the ring is I say r. That is how much? That is 0.5 meters. 0.5 meters. Moment of inertia of a ring, you understand mr squared. mr squared. mr squared. That's important. That's important. So in this case now you can do it. Again conservation of now because there is no resultant torque acting in the system. Then apply conservation of angular momentum. If there is no resultant torque, before total angular momentum must be equal to after total angular momentum. Conservation of angular momentum curve before total angular momentum. The equation for the angular momentum is I omega. Angular momentum equals I omega. I omega. I1 omega 1. I1 angular momentum omega. Total moment of inertia after I2. Angular momentum I see omega 2. Angular momentum I see omega 2. Omega 2. Omega 2. Then I should find omega 2, right? Now here I have to find omega 2, I think. Now they are asking angular momentum, but they are asking angular momentum, but it is mistaken. That's wrong. Look at the answers. Answers they mention omega. So therefore we need to find the angular velocity. You need to find the final angular velocity. You need to find the omega 2, right? Question is wrong. It's not angular momentum. They are asking angular velocity after angular velocity. Then I1 omega 1, I2 omega 2. I1 is 2. I1 is 2. Omega equals I2. Total moment of inertia. Total moment of inertia. 2 plus moment of inertia of this ring mr squared. Mass is how much? Mass is 4 kilogram. R. Radius 0.5 meter. 1 over 2 whole square. 1 over 2 whole square means 1 over 4. 1 over 4 omega 4 4 cancel out. Here 3 omega 2 equals to omega. Omega 2 equals to omega over done. That's also done. Right. Time is 11:05. Okay, look at it 2010-11. Now we'll quickly come 2010-11. 2010-11. Raise your hands. How much you understood this question? Understood. Understood this question. Understood this question. Understood this question. Raise your hands. 2010. Right. Indian. 2010 level question number. 2010 question number 23 in your page number 23 in the paper. 2010 paper question number is 8. 8 is 8. Number 8. 8. Now they have given a graph that says that if the angular velocity of an object varies with the time as shown in the figure, angular velocity time graph. So what is the equivalent graph in linear motion? Velocity time graph. Velocity time graph. Corresponding variation of angular displacement. They given omega t graph. Omega e graph is given. You know the corresponding theoretic graph. Very easy. Angular displacement time graph. It seems like angular velocity means in linear motion velocity. Angular displacement in linear motion is displacement. You want to convert Vt into ST. Vt into ST. Now, how do we convert Vt graphs into ST graph? Now, with Vt graph, gradient, Vt graph, now in Vt graph, gradient. Now, what happened to look at what happened to the y-axis in Vt graph? How do we convert Vt graph into ST graph? What happened to y-axis should happen to the gradient in ST graph. How do we convert this one? What happened to y-axis in Vt graph should happen to the gradient in ST graph. Gradient in ST graph. The what happened to the y-axis? Positive y increases. Then positive y increases means positive gradient increases. Am I correct? Positive y increases means because velocity increases, positive velocity increased. Because positive velocity increased, then your gradient, positive velocity increase means positive gradient increases. Am I correct? The positive gradient means acute angle. Acute angle increases. Raise your hand, somebody understood. Then important things now. Vt graph now. Vt graph gradient represents acceleration. Area under Vt graph represents displacement. So what about the angular velocity? Angular velocity time graph. Gradient represents angular acceleration. Area under angular velocity time graph represents angular displacement. Right? So you know it's discussed. Then we'll go to question number That is also this one 10 A level. That's easy. 10 A level question number 32. 32. 32. This case. This case. Now this is also very easy now. Now tell me the right answer. Tell me the right answer for this question. It says that if the moment of inertia of an uniform cylindrical rod about the axis A, B, and C shown in the figure are IA, IB, IC respectively. Tell me the answer. Everyone tell me the answer. Everyone tell me the answer. Quick. Tell me the answer for this question. So I always say that these questions are not difficult. If you trust, you believe on yourself, and you continuously keep on funding, you get the result. People who think they can, people who think these things are not compulsory, they will struggle. You will see, they will struggle. And I'm not such a part of Aryan. Volume decreased. It's lagging. It's lagging or volume decreased. See what happens. Now still same. Now it's fine. Now it's okay. Right. Now they have given three axes name A, B, and C. This is A axis. Axis A. Axis B. Exactly. Axis B. Axis C. Now I don't need to explain. Reply what is the right answer. Now you guys can tell me the right answer. Reply in the chat box what was the right answer. Reply everyone what was the right answer. Reply everyone what must the right answer. Now we know that now. Now which axis of rotation have larger moment of inertia? The larger moment of inertia belongs to C. From the axis of rotation linked to the last edge of the mass is I. Large moment of inertia belongs to IC. Small moment of inertia belongs to A because mass distribution is very small from the axis of rotation. In between this idea. Raise your hands if you understood. Raise your hands if you understood. So look about that idea. Next question, 2011. 2011 question. 2011 question. 2011 question. I think there is no issue in my voice, right? Usual voice, right? That you don't hear some sort of reduction in voice. Now, when you increase the your what sound you use, the way that you usually hear, you are hearing really right. Ah, hit by someone? Yes. 2011 question. Mm, in this case, question number very easy. So if you practice these questions and if you do your school term test exam, they are not difficult. You see, whatever I promised, I have done some of 30. 2011, 30. Now again, conservation of angular momentum. By looking them, you can see you have to apply conservation of angular momentum. Conservation of angular momentum. Conservation of angular momentum. It says that space shuttle capital B of moment of inertia I, angular speed omega 2, joins smoothly with the space station capital A of moment of inertia I1, angular speed omega 1, along with the common axis as shown in the figure. Neglect the linear motion of both objects. The angular speed of system about the common axis after joining the two objects. It seems like now something is kind of type of idea. In linear motion, we learned that now there are two masses m1 moving to the, let's say, m1 is moving to the m1 is moving to the, let's say, now I can't see the direction of rotation. Both are clockwise or anti-clockwise. That is important. So I can't see in that given diagram the page route, they are rotating, both are rotating clockwise and anti-clockwise direction. Seems like now look at here now. I mark both of them moving anti-clockwise direction. I assume now when I get the answer, understand, I assume that both the disk, both the objects are moving in anti-clockwise direction. In case if one is rotating in anti-clockwise and one is rotating in clockwise, then it's completely wrong. Different idea will be coming. But I consider both of them moving in anti-clockwise and I'll get the answer, right? This is very equivalent to there are two masses m1 and m2 moving in same direction. Let's this one's velocity is v2, this one's velocity is v1. Let's say v2 is larger than v1. So what will happen? This m2 will collide with simple m1. After the collision, let's say system get combined. M2 and M1 stick together and both of them are moving. The combined velocity will be, let's say, v. Then you know how to apply it. If you consider if there is no resultant force acted on the system before total momentum, M2 V2 plus M1 V1 equals M2 V2 plus M1 V1 equals M2 plus M1 capital. The same idea here. The same idea is used here. Same idea is used here also. Now, two disk. Angular velocity omega 1. Moment of inertia of this disk is I1. This one is rotating under omega 2 angular velocity. Moment of inertia I. Then now I considered both of them are moving in anti-clockwise direction. Then what is the total? No, angular momentum is a vector. You know, angular momentum is a vector, right? Angular momentum is a vector. So therefore, direction of this vector is also upward direction. You know how to apply the direction upward. This one is also having angular momentum in upward direction. This one's angular momentum is how much? I1 omega 1. This one's angular momentum will be I2 omega 2. Then I1 plus omega I1 omega 1 plus I2 omega 2 is the total angular momentum of the system before they combine. After they combine, after they join, after they join, system is moving on, let's say omega angular velocity. Then what is the total moment of inertia? Total moment of inertia will be I1 plus I2. So what is the total angular momentum after they merged? Total moment of inertia is I1 plus I2. Angular velocity after they merge is omega. Then you can define the omega equals I1 omega 1 v I1 omega 1 plus I2 omega 2 over I1 plus. Now in case because I could not see the diagrams clearly, if this one is moving in anti-clockwise direction and suppose if this one is moving clockwise direction, in MCQ they can test. This one is moving clockwise, this one is moving in anti-clockwise direction. In that case, directions are different. Direction of angular momentum is in upward direction for this one. Direction of angular momentum for this one is in down direction. Therefore, I1 omega 1 minus I2 omega 2. That idea. Now, ratio and up to everything is very clear. Yeah, how many questions we discussed so far? If that take, how many questions? How many so far? Someone say how many questions that we discussed so far? Right. So then we are discussing 2012 A level, 2012 A level, right? 2012 A level. So when you hear a lack in my voice, it's what? Breaking, let me know. 2012 A level. Question number 24. 2012 A level. Question number 24. 20, 20. Now this question. Now understand now. When I was explaining one of the gravitational field essay question, I told you that if an object is moving in a elliptical motion, and remember, if an object is moving in elliptical motion, I told you that we can't apply general, we can't apply what? We can't apply rotational motion equations. Because why? That is moving in angular, that is moving in, sorry, we can't apply circular motion equation. Okay, my bad. Okay, I will explain this question detailing. I will explain them detailing. Uh, I will explain them detailing. Look at this question says that satellite moves in an elliptical orbit. It's not a circular orbit, elliptical orbit about the Earth capital E. Speed of the satellite at point capital A is V. Speed of satellite at point capital A is V. Then its speed at point capital B will be. Then its speed at point capital B will be. The diagram, some data is missing in the diagram. Okay, in that page to that diagram, some data is missing. Very carefully see. Now this is also you need to put some short note regarding this question. That very carefully see. Very carefully is very important question. Now elliptical motion means we know that distance from the center to different locations of the object in the elliptical motion, that's different. Am I correct? Suppose if your object is somewhere here, distance to the object from the center of the elliptical orbit is they given capital D. Capital D. They given capital D. This data is missing in the page book, right? When the object is somewhere here, distance to the object from the center of the elliptical orbit is 4D. Is 4D. Is 4D. 4D. Right. Right. Now this object is rotating. It's rotating actually, but understand when object moves in the elliptical motion, we can't apply circular motion equations. First important point that you should mark in the short note is when object moves in elliptical motion, we can't apply circular motion equations. F equals mv to the center. Why? R is changing because different location of the object in the elliptical path, distance to the object from the center is changing. Therefore, generally we don't apply F equals ma mr omega squared v squared over, we don't apply. But understand, any rotating object, conservation of angular momentum can be applied. No matter the object is moving in a circular motion or rotational motion, conservation of angular momentum can be applied to any rotating object. Then can you remember I told you there are two equations to find the angular momentum. Capital L means I omega. The most popular equation capital L is I omega. Most popular one is capital E equals I omega. Now we also understood all the time that we use capital is I omega. But we apply, but rarely we apply L equals mv into R. Now I clearly given these equations in your note. L equals mv into R. Now understand, when the object is at here, tangential velocity, let's say, it's not vertical, tangential, you can understand that. Tangential velocity has been given. It's V. Point A, it's V. It's our point A. Now we need to find when the object is at point capital B, we need to find the tangential velocity, I think, right? I say it's V. Now my target is finding VB. Now there is no any resultant torque acting on this rotating object. If there is no resultant torque acting on this rotating object, we can apply conservation of angular momentum. When the object is at point capital A, angular momentum must be equal to when the object is at point capital B. When you apply conservation of angular momentum, when the object is at point capital A, angular momentum, mv into r, mass same mass, velocity at point capital A, v, distance, the ray distance from the center to the point A is 4d. Must be equal to when the object is at point capital B, angular momentum, mass same, velocity that is vb. I want to find vb into r is d. D cancel out, cancel out, 4b. VB equals 4b. 4b. 4. Right. 11:30. Right. That is also done. Okay, we have small questions to discuss. Okay. Okay, we'll discuss remaining next week. We will discuss remaining. So the homework is read this question again today. Today and yesterday also will some more questions. Read them again. Send me today as a video. Okay. We'll meet on not tomorrow, maybe